Okay, so that was one question we wanted to get answered today. How do you transform a truck into a rocket? Our next question today, of course, is why would you hack and how would you hack a Tesla Model S? Well, the gentleman who's going to answer that is here to do that now. He's the co-founder and the CTO at Lookout, and I think he is there. Give him a round of applause, ladies and gentlemen. This is Kevin Mahaffey. Kevin. Hey, there you are. Come on out.
Perfect. All right.
They've got a little bit of housekeeping here to do and setup too, so guys, do what you need to do.
All right, so we're going to get set up right now, and hopefully it all works correctly. Perfect. So that actually is the sound that a Tesla makes when the door is left open. We extracted the audio file from the firmware, and if you think it's bad listening to it for 30 seconds now, imagining for 8 hours straight, just... All right, perfect. All right, so I'll get started. So I'm going to tell you today, as was promised, why I decided to hack the Model S, and what we learned that actually can apply far beyond just this car, far beyond even the world of connected cars, but to all Internet of Things and IT systems in general. So what happens if you don't do this right? Jeep suffered a hack, a security issue over the summer, and instead of being able to fix the issue very easily, they were actually forced to recall 1.4 million cars. In contrast, the issues we found in the Tesla, they pushed an over-the-air update, the owners had to push one button, and the problem was fixed. Cybersecurity is a very, very big issue if you do it right, or if you do it wrong. It can massively impact the course of business. But first, why did I undertake this research? It was myself, Kevin Mahaffey, and my research partner, Mark Rogers, have been working on this project for several years. And we decided to look at the security of connected cars for several reasons. One, because there are so many connected devices in the world, both things that you use personally and that are used in the heaviest industries and the most important industries in the world. And Gartner estimates that there'll be over 25 billion connected things in the world by 2020. That's a huge number, far more than there are PCs and far more than there are mobile phones. But PCs, mobile phones, servers are not the same as connected things. When we build connected things, they're around for a very long time. You replace them much, much more slowly than you do computers. And at the same time, it's not the same industries producing connected things as we had software in the past. These are brand new industries. And a lot of these industries are not software industries. They don't have security teams. They don't have years and years of experience of existing on the internet. And when a new industry builds a connected thing, you can ask a question. That question is, are there best practices? If there are best practices, things go well. If there aren't, they go badly. So if there are no best practices, you have companies kind of going about their business, doing things that they already have, and they march swiftly to their doom, not knowing why all of a sudden they're in a bunch of trouble. If there are best practices, even though the company may not have a lot of experience in cybersecurity, they can get a lot right just by following what those best practices are. And early in an industry is the best time to do best practices, particularly when you have something as complex as the Internet of Things of the automotive industry, when you have OEMs, manufacturers, and different vendors all collaborating. If they have the same principles and architecture in mind, then they can solve these problems. Whereas if they're all marching to their own drum, not really realizing what's going to happen, it's just a total mess. And of course, now is a lot easier as connected vehicles are just starting to come to the road than 10 years from now when you have every vehicle is connected and we're trying to go patch a bunch of vehicles that are already out there. Always easier to engineer things in the beginning than at the end. And so for connected cars, that's now. Of all the connected cars we could look at, we chose the Model S for one reason. Because it was architected from the ground up, it really doesn't have a legacy. And we had the hypothesis that they would be doing a lot right in the car. So even though we tried as hard as we could to hack it, that we hoped we would find things that we can showcase of here's what they did really well. That actually turns out to be the case. So they did a lot of things well, but they also did a few things wrong, and we're going to take a look at that. But the most important thing is that the things they did not well, they fixed extremely quickly. And the lessons I'm going to talk about apply not only to the things in your house and your daily life, but also to enterprise endpoints, the smartphones and tablets, PCs, laptops, and servers. And as it turns out, a lot of the same security learnings people can apply in their IT or their operational technology, ruggedized devices, industrial control systems, and whatnot. And some very, very simple mechanisms can actually massively impact the likelihood of getting hacked. But first, a public service announcement. When you're hacking cars, it's not just like a computer. The worst that can happen is actually quite bad. So it's very important to undertake safety precautions when undertaking security research. I won't go into all of the precautions that we took, but we had a very, very strict set of ethical and careful guidelines that we set out for ourselves when we undertook this research. I would urge you to think very, very carefully whenever you do this. So onto the Tesla. The Tesla Model S is a fascinating vehicle. There are 2 Linux servers in it and 1 real-time operating system. And you might be surprised to hear that there are actually 3 separate server computers in this car. This is not a car, it's a data center on wheels. The different subsystems are the center information display. So I'm going to use the word CID throughout this talk. The CID is that thing in the middle, the big 17-inch touchscreen. The instrument cluster, the IC, and then the gateway is FreeRTOS. From a systems architecture perspective, you have 2 networks in the car. You have the CAN bus, which is where all of the highly sensitive vehicle systems are, and which is where your brakes are controlled, your airbags, your gas, all of that. And then you have the infotainment network, which is where the IC, the CID, and the gateway live on. And the gateway is the thing that bridges the 2 networks, as the name might imply. A little bit more detailed, you notice all of the external networks, the Wi-Fi, the cell service, Bluetooth, are on the infotainment network, not on the vehicle network. That'll be important later. And they're all connected via an Ethernet switch on one side and basically a CAN bus on the other side. So when you're undergoing an attack, the first thing you need to do is inventory. So I'm going to tell you the story about how we actually were able to breach the car, and also a lot of ways how we failed and how a lot of the security mechanisms were quite good. So first, undertaking an attack, we needed to take the car apart. This is a piece of hardware. So you need some of these security bits. You get them for not too much money from Amazon. And you need some of these pry bars to pull open the door panels. So the first thing we did is to try to take out the instrument cluster and the CID. We're pulling out the door panels. You can see us taking apart my co-founder's car. We were very, very careful because Tesla Model S's are not cheap. And you can see we're kind of very carefully shimmying open these panels. And these things are evil. If you've ever taken apart a car before, you would have seen these door panel clips. And the problem is they take 10% more pressure than you think is going to break them to pull them off. So you're pulling, you're like, okay, I can't pull anymore, it's going to break. And you just have to go 10% more, and then they pop off. And so it's like this nerve-wracking experience taking apart a $120,000 car. But we did it. We didn't break anything. And so this is the back of the instrument cluster. So we disassembled it. This is the PCB, the front side of it. What you'll see is an embedded computing module on the front and something on the back. We're effectively looking for things we can hack, memory cards, headers, things we can get into. Unfortunately, the IC didn't have very much. And then we took apart the CID. The CID had a lot more connections, and it was a much more robust PCB. Here's the back of it. And it has a memory card and another memory card. So we've got 2 removable memory cards. OK, these are great places to start. We also found a USB port on the side. Also great ways to get in. Let's see what we can do. And then, interestingly, under the steering wheel, we found this very odd little port. We had never seen this connector before. Who knows what it is? So hardware inventory, we have 2 memory cards. We've got a USB port, and we've got some weird carryable, who knows what it is. And then so we went to the software inventory. First, there was a web browser, so that's the first thing we took a look at. And it's based on Qt. The name of the user agent is Qt Car Browser, and it's running WebKit 534.34. And the good thing about WebKit is it's open source. We actually looked at 534.34, and you can actually see it's 4 years old, right? And that's really significant. And we said, OK, why are they running a 4-year-old version of WebKit? Well, if you look at how the patch process works on WebKit in this car, it's very similar to how the patch process works on Android devices. So WebKit is the open source project behind Chrome, Safari, many, many, many web browsers. In this case, it goes to Qt WebKit, which is the Qt wrapper for it. And then finally, Tesla pulls from there. And so if Qt WebKit is out of date, Tesla can't actually get a newer web browser. And that's a really big problem. So anytime you're building connected things, you're reliant on your upstream open source projects. If they have vulnerabilities, then you have vulnerabilities, and you need to make sure to patch them. And we actually found a whole bunch of vulnerabilities in this browser. We were able to get the browser to crash reliably, but we were not able to get remote code execution. It's quite hard to do remote code execution when you actually can't debug the device. So we kind of stopped there for a second. We said, OK, maybe there's something, but let's try other routes. But a pause here. We have a lesson that we learned. And the lesson we've learned is because you have these connected things using very popular open source projects that have many vulnerabilities discovered in them, you need a patch process. If you look at how Apple runs their patch process, very simple, one click. Look at how Microsoft runs their patch process, very simple, one click. And even servers, automated orchestration is a best practice in all large server deployments. When there's a bug in an open source library, you can push a new version of all your virtual machine images, all your containers very, very quickly. Even tablets and smartphones, patching is a best process. There's a one-click update process for all of these. But things run all the same software as all the other endpoints. Yet manufacturers typically treat it as a black box firmware that you might maybe figure out if you're lucky enough on their website where you can download it. It's not a one-click process. And it's not software controlled by you as the owner, whether it's an organization or you as an individual. And that's a big problem. Though Tesla did something very different. They have an over-the-air update process. That's one click to an end user. You do not have to subscribe to a data plan, which is really important. And they update rather frequently. Here's that one click I mentioned. But you might ask, well, why isn't everyone doing that? And the problem is, it is truly an economic problem. So hardware manufacturing effectively costs money. And when hardware manufacturers ship products, they make money, right? And when you look at this as a recurring process, as a business process, it's profitable, right? It's great. But now you add this little wrinkle of software updates in, and software updates cost money. And you do it over and over and over again, and now it's an unprofitable business process. So no wonder many manufacturers don't do it. In my opinion, I think there's a way out of this trap, is that if we transition the software sides of Internet of Things business to services businesses, all of a sudden you have a service that creates money. And when you treat that as a business process, you do it over and over and over again, it's a profitable process. So the things you do to make your service better, richer, make more money is also how you get security updates in there. This is my preferred way and how I think the majority of the industry will evolve. But there are other ways to do it. You do have quality-oriented brands who will do the right thing. But unfortunately, not cost-oriented brands. These are the brands that the $20 Android tablet, never going to get an update. Could solve it with regulation. We could have market forces where people buy secure things and not insecure things. That's also hard. And I think it might work in the enterprise, but in consumer where people are very cost conscious, may not work well. So OK, back to probing the Tesla. So those memory cards, you remember those? One of them had a fat file system. It had effectively a file on it called car keys, and it had a bunch of private keys in it. That's kind of funny to me that the future of car keys is public key encryption. It's not a little thing that you plug in. I think that's kind of fantastic. And remember that mystery board I mentioned? Well, we probed it with a bunch of wires. Turns out it's just Ethernet in a non-standard jack. So now all of a sudden we have access to the internal LAN. So of course we're going to map it using a tool called nmap, very common. And this is just a sample of all of the things that are running on one of the systems. It's a huge number of open services. If you were paying attention, you may have seen one of them was X11. X11 is a window management system. So this is about 3 in the morning one weekend, and we decided to have fun with these open X11 servers and decided to take over both the instrument cluster and the center information display. You could inject arbitrary data onto both screens via these open patches. And then we looked at some of the other open services to try to see what other information is out there. This is what's called the IC updater. Does what it says, it updates the IC, and it outputs tons and tons and tons of diagnostic information. So for someone who's trying to hack a system, this is perfect, right? You just get all sorts of rich data about it. And you'll notice there's one very, very, very interesting thing. There's an internal URL that's a handshake. Like, okay, that's not publicly accessible. We know there's something fun there. But we had a setback. So remember that Ethernet port? The internet found it. Other people on the internet found it in parallel with us. And Tesla issued an OTA update, good for them. But unfortunately, they blocked access to the Ethernet port. So crap, what do? The good thing is, we've been already on the network, and we know it's a switch network. And so any switch network, we built this very high-tech, very precision piece of engineering into the back of the instrument cluster, and effectively hooked it up to a switch. So we basically kind of man in the middle, hooked it up to a switch, and now we had our car LAN is extended out, to the side of the car on a Netgear switch. And now we're back on the network. So one day we're poking around, and that IC updater, that CID updater, showed a firmware download URL. Okay, this is a jackpot. This is what we've been waiting for, because we didn't have access to firmware before that. And then we used the car keys. We found out these are keys to an OpenVPN connection. By looking at the network traffic, we knew they were sending an OpenVPN connection to their servers, and we got into it. And we were able to download the firmware, all 646 megabytes of it. Fantastic. So we got around to examining that firmware. And what we do is found that is squashfs, which is just a compressed file system, very easy, pretty standard. Now the question, to the security folks in the room is, you have a file system, what do you do? Typically the first thing you look at is private keys. Unfortunately, we didn't find any encryption keys, so okay. The next thing you look for is shadow files. We found one for the instrument cluster. And for those of you who don't know what a shadow file is, this is the file that stores your encrypted password. So when you type in a password to log into your computer, it doesn't just store that password in plain text. That would be rather silly. Instead, it stores an encrypted version of that password. So when you type it in, your computer encrypts that password and then compares the encrypted version. So the shadow file in and of itself is not usually useful. Usually you need to crack it. So we tried to crack it. And I was getting ready for like weeks and weeks and weeks of password cracking. But 10 minutes later, the shadow file cracked. It actually turned out it was a really, really, really weak password that just my laptop cracked in a few minutes. And so now the question is, we can log into the machine. This is fantastic. But that's just an unprivileged user account. Crap, well, how are we going to actually get root on the machine? And that's usually what you do. Once you get into a given system, you say, well, how do I get super user access? Well, as it turns out, the cracked account was what's called a sudo-er, which is you just ask for super user access and you get it. Well, this kind of sucks. Oh yeah, that was anticlimactic. So the next question is, well, how do we get to the CID? That's where a lot of the, all the network connectivity happens. That's really, really important. There was no CID shadow file. So what do? How are we going to get there? So we went back to the firmware mines and started toiling away. And we found, actually interesting, that there's this concept of a security token. And the CID will retrieve a new one from what's called the mothership, which is Tesla's internal server infrastructure, every 24 hours. And then the CID has an account called Tesla One, which it sets the password as the security token it gets from the mothership. OK, that's interesting. But then it tells the IC what the security token is. And the IC stores that in plain text on disk. And if you remember, we have root on the IC, so now we can get it. As it turns out, we could use that password that was stored on plain text in the IC. Now we have full access to the CID. And guess what? Also a sudo-er. So we have root on both systems. And it's interesting. So from the instant the firmware download was done, to having root on both systems was like 2.5 hours. Yet to get all the way to access to that first system was like years of work. So it shows you how important it is to not just rely on external defenses. And this is, by the way, how almost all internal enterprise networks work today. Bad guys spend so much time trying to get in. Once they're in, it's easy. If they're in one of your systems, you get on one laptop, one phone, one computer from a vendor, you access the whole network very, very typically. And this is the problem with the way enterprise networks have historically been architected. They're architected to create this sterile environment with big walls on the outside. I like to look at biology because, as it turns out, our bodies are constructed somewhat similarly. I stole this diagram from a journal, Nature, and this is the immune response in your skin. You think of your skin as a barrier to keep pathogens out of your body, but it is not simply a barrier to trying to create a sterile environment. You actually have a very strong defense in depth both inside your skin as well as inside your body. And what happens if you don't have this immune response is you have to live effectively like the bubble boy, who is known for having no effective immune response and had to live in a sterile environment. And unfortunately, he did pass away because something got through the barrier one day. I think he was like 18 years old, and he passed. And this is a security principle that I think everyone needs to take to heart, is when you have absolute trust on an internal network or anything you think is sterile, you will be hacked absolutely. And there's a way out of it. And a lot of companies are changing the way they're solving security from this format of absolute trust to more of an immune response. And it first starts with hardening individual components. Each individual system must be secure. So for example, if I hacked the IC, I should have no privileges on the CID. Unfortunately, that wasn't the case in this case. You have to assume attacker will get behind your perimeter. Number two is the concept of data-driven feedback loops. So when I'm mucking around there, I'm doing things that the car should ordinarily never know. The same thing what happens if I hack into a web application or a hacker gets into your web application, they're going to do things against your databases that a normal user would never do. But unfortunately, most people don't have the data feedback loops to detect and to realize that's happening. And it is, you want to detect and respond to compromise. This is actually not a new idea. Please don't read all this slide. There's actually a lot of information on it. It's called the OODA loop. Many of you might be familiar with this. And it was actually developed by a fellow named John Boyd during the Vietnam War to describe F-86 Sabre air-to-air combat. And this model was effectively used to try to describe how two opposing fighter pilots how to conceptualize who will win in this dogfight. And the key realization was the pilot who could observe, orient, decide, and act faster than their adversary to predict what their adversary is doing would almost always win the dogfight. So the key learning there is to decrease your cycle time. As it turns out, enterprise security, a lot of organizations are moving to a very similar architecture. It's hard to pronounce that OODA loop doesn't have the same ring to it as OODA, but essentially you acquire data from humans, sensors, otherwise. You enrich that data, you analyze it. You decide with humans or machine learning, and then you act, either with humans taking action or with automated orchestration, automatically blocking things. And just like in dogfighting, if you as an IT organization can iterate your loop faster than your adversaries, you can win. You have to assume people can get in, but if you can detect them and respond to them faster than they can do anything, you win. Doesn't matter. So back to controlling the vehicle. So we had full access to the CID, full access to the IC, but what about that gateway? We really want to figure out if we can actually do something to the vehicle itself. And so we decided to say, OK, let's reverse engineer some of this network traffic to see how the instrument cluster and the CID are actually controlling the vehicle itself. And so we triggered a bunch of events, and then we watched for traffic, and we built some tools that would actually suppress a lot of the traffic, because there were like 10,000 events a second happening on this thing. So we said, OK, we were only looking for unique commands. And it turns out that we found where most of the commands were happening. But it was just a black box. It was just a binary payload, so it was kind of hard to understand. So how do we construct those packets? Well, as it turns out, we found where in the firmware the software was actually generating these packets, and we reverse engineered it. And if you see some words up there, you'll see VAPI. That's really important. That's an extremely good security architecture. We never saw the word CAN anywhere. If the car, the instrument cluster, the CID, were sending direct frames to the CAN bus, that's terrifying, right? That's your radio, your internet browser telling the brakes what to do. You don't want that. We didn't see that here. We saw this thing called VAPI. As it turns out, the gateway has an API, the vehicle API, where it constrains what functionality the infotainment system can send to the vehicle. This is fantastic, and actually very different than what happened with the GPAC over the summer. With the GPAC, that infotainment system could directly talk to the brakes. Not good. But in this case, there was a constrained set of functionality. But of course, we're hackers. We didn't want to just stop there. So I think there's a lesson to be learned here. So just like your brain, you have a blood-brain barrier. What that means is even though you have skin to try to isolate your blood and your internal environment from the outside world, you also have a blood-brain barrier to isolate your blood from your brain. That further stops pathogens from getting to your critical assets. And I would argue that your brain is probably the most critical asset, like many enterprises' really, really core data sets. In IT, actually, airplanes are architected the same way. You have in-flight Wi-Fi. The in-flight Wi-Fi system, you cannot talk directly to the avionics system. However, the avionics system can, in isolated circumstances, give data about the altitude, the airspeed, the GPS location back to that in-flight Wi-Fi side. So they're not completely isolated. There's this very, very, very isolated set of things that can go back and forth. And if you look at the way the Tesla is architected, if you look at the CAN bus, there's only one thing that can talk to it, and that's the gateway. So this gateway is what isolates the really, really sensitive data, the really, really sensitive functionality from the potentially untrusted but still reasonably secure infotainment network. In IT organizations, this might be your customer data, social security numbers, financial informations. That is your really, really sensitive data here. So back to controlling the vehicle. We can control anything that the CID can do. So any of the buttons you can press on that information display, we can now do programmatically. And so now we have started to ask the question of, what might this VAPI do? Are there any pieces of functionality in the VAPI that would allow us to do things at unexpected times? Because all the functionality you can do is for legitimate purposes, but if you think about all of these things you can do, are there any that stick out at you as things that you might not want to do at certain times during driving a vehicle? So we set up an SSH tunnel between the CID and an internet server. So we effectively put a Trojan horse inside the car. We can remotely control the car from a terminal, even without touching it. But important to note, this was physical access first. This is not just, hey, you can go hack any car in the world. That's an important thing to note. And we can SSH into our car. And so this is my research partner, Mark, and you can see what we did. Oops. Hopefully. There we go. And this was an abandoned parking lot. This was not in any public area. So if you do test a car, I would encourage you always to do it away from other people. My favorite song. So what you just saw there was Mark SSH'd into the car directly, and while I was driving, effectively issued some commands that would turn off the car, and you saw that it lurched to a halt, and then all the screens just went black, and so I'm driving down the street and just the car stopped. The interesting thing we found is below 5 miles an hour, it would immediately apply the parking brake, but above 5 miles an hour, we didn't test it above like 8, so it was pretty safe. You still had control over the car, but the parking brake would not turn on. Presumably for safety reasons, if your parking brake slams on when you're at 30 miles an hour, that would be bad. And so conceivably, you can pull the car over to the side of the road and stop it. So we were actually impressed, even though we were able to turn off and disable the car's built-in mechanisms sanity checked it and said, okay, hey, I'm going to apply the parking brake in this situation, not in these, but in all circumstances, I still had steering control, which is pretty good. So again, I want to emphasize this was not a remote access exploit. It requires physical access. And the reason why that's important is people have demonstrated you can get remote access to any web browser, any system. That's not the focus of this research. So we don't want people to go around and saying, every Tesla is hackable and you can stop all the Teslas, blah, blah, blah. Theoretically, any system that is possible, that's not what we focused on here. So, what did they do? What's the lesson learned here? So how do you respond? So Tesla actually was able to, from start of rollout to finish, roll out to their entire fleet of cars in 1 week. That's incredible. And it fixed most of the secure vulnerabilities. And also they increased some of the hardening between the browser and the internal systems, which is great. And it also actually further restricted access to that gateway in that principle of, defend that brain from even from the blood. They tightened that down. And I know that since that original update that was in August, they've been continually working to really, really harden it. And actually, when we originally presented some of this research, that's J.B. Straubel, the Tesla CTO, he actually came to DEF CON and said, hey, thank you. And by the way, and they encouraged everyone else out there to say, please hack our car responsibly and tell us about it because we want to know about it. They actually even pay hackers. They will, if you submit a bug, anybody in the world can do this. You submit a bug, you follow their guidelines, they will actually pay you and say, thank you for doing that. This is in contrast to how some other auto manufacturers have responded. So in the US, we have this thing called the Digital Millennium Copyright Act. And what that is effectively, it describes what sort of security research is exempt from prohibitions against reverse engineering and circumvention. And the Library of Congress decides, I believe it's every year, what circumventions are allowed and disallowed. And there were many automakers who actually were lobbying the Library of Congress in the US to make security research on cars illegal. So again, if you saw how Tesla, they came to DEF CON and said, please hack our cars. A lot of other manufacturers say, hey, we want to make it illegal, right? Which, from my perspective, is silly because criminals don't follow the law. So anyone who's going to do bad things isn't going to be able to do it, but university researchers aren't going to be able to do it. It doesn't help, right? The game theory of it just doesn't make sense. So, but we'll work on that. So luckily, the Library of Congress actually said, no, the public benefit of security research on cars is good. We want universities to be able to do this ethically. Sorry, it's going to be an exempt, so that's fantastic. So summary, what did we find? This diagram is interesting. It's called the kill chain. And also, like many things in security, it comes from military theory, which is to say, what are the sequence of events you need to do from point A to reach your tactical goal? In this car, we said, well, the tactical goals are either to disrupt the driver instrumentation or disrupt the vehicle. And we actually mapped out all of the different ways we can get between the systems to do that. And so if in any sort of IT organization, you're building your threat model. You say, hey, this is our sensitive database, or this is our financial trading network in the case of an investment bank. OK, what is the kill chain, or what is the threat model to there? And almost always, you're going to have way too much to do in security. I've never met a security organization that said, wow, we've finished our roadmap. We can all go on vacation now. Almost always, you have to prioritize. And the reason these threat models and kill chains are really important is because you can say, OK, with your limited resources, where am I going to invest? And if you imagine here, you know why Tesla is working so hard to secure that gateway is, well, that's, if you disrupt access to the gateway, the kill chain is disrupted. Maybe you can hack the browser and display some funny web pages, but if you can't hit the gateway, great. Right? And so that's a really, really helpful way to look at this. So what did they do right? I mentioned OTA process, key attributes, fast, no cost to the end user. They didn't have to pay for self-service, and had a one-touch or a no-touch user experience. They had isolation between the gateway, that blood-brain barrier we talked about, and there were no direct access from the infotainment to the CAN bus. But they had some things they needed to do better. That perimeterized security model, remember, it took us a long time to get in, but once we were in, it was like a couple hours to get from unprivileged access on one system to root on the whole thing. That was not well done. And they, as part of their patching, they've actually changed that and have improved the way they isolate individual systems. So even if you hack one system, that shouldn't matter. We have to assume a browser will get compromised, the Bluetooth stack will get compromised. That's just how systems happen. If we're designing to assume that we have to live in a bubble, that's no bueno. And the lessons that we can extract for everyone in the room here. So number one, software updates. If you're a vendor, if you build things, if you build software, make sure you have a good update process. Don't just do black box firmware, hide it under the support section of your website. Users won't apply it. It has to be no touch or one touch, and you have to do it really frequently. You have to solve your business model issues. If you're not solving your business model issues and you're just advocating for budget internally, yet you might be powerful enough today, but at some point the organization's immune system is going to attack things that are cost centers, that they always do. So try to make this part of your business model, not against your business model. The security immune system. Hardening individual components and building that ADA loop, that data-driven feedback loop where you're inspecting all the things, analyzing it, deciding upon it, and then automatically, in some cases or with humans, responding to it. If you don't have that, somebody's going to get in and you're not going to know for years, or you're going to read about it on the front page of a newspaper. That's a problem. And remember that blood-brain barrier. Build a blood-brain barrier, identify your critical systems, isolate them, and really focus your efforts on disrupting that kill chain, particularly against your really, really critical systems. And with that, thank you very much. Appreciate it.
We have time for maybe one or two questions. I think I've had about 15 people ask me to ask you.
Yeah.
Why did you do it?
Well, I think that after hacking something, you try to make it better, and those lessons are universal. And I know I've spoken to many, many people who are actually applying some of the things we talked about in their enterprise networks for Internet of Things, and my hope is that I don't have to give this talk again. on a different vehicle.
You know, there's also the talk about there are the good hackers and the bad hackers.
Absolutely.
You characterize yourself as a good hacker.
Usually.
I would assume. Usually. How do you end up falling into the good hacking category? Because I mean, it would be easy to be a bad hacker too, wouldn't it?
Yeah, so the issue with good hackers and bad hackers, I think it a lot of times comes down to economic opportunity. I was fortunate enough to be in a time and a place in a country where there were opportunities to put skills for good. But if you're in a place where there are not those opportunities, you have the skills and you need to eat. So you know, it's going to happen. I mean, I think hacking I think is not different than crime.
Sure.
We're not going to solve crime anytime soon. We haven't in the course of human history, but we can make it so that it's so rare or so infrequent that it's not a huge drain on society.
Yeah,
that's the goal.
Okay. Questions from the audience? We have time for one question. Anyone? If not, no? Sure? All right. Kevin, thank you very much. That was a great presentation. Thank you. Give him a round of applause, everybody. Kevin Mahaffey. Excuse me.